So we did a bunch of different graphs yesterday. Okay, I think 1 through 5. They were all the same function. We were just looking at different intervals. Thank you. And we're just going to jot down some things that might be noteworthy from those 5 different graphs. So the first thing I want to make note of is just the main idea of what we did yesterday. If we have an integral from a to b of some function, when we evaluate that, this is the area under the f of x graph from a to b, measured to the x-axis. Okay, so you're always shading to the x-axis. We're going to eventually see some examples by the end of the year where we shade to the y-axis. We'll see how that changes a little bit, but for now it's just to the x-axis. Now, depending on the number value that we get from this integral, that kind of tells us something about where the area is located that we shaded on the graph. So there's 3 other things that we're going to check out. So we'll write down 2, 3, and 4. What if the area value we get is greater than 0, meaning a positive number? Okay, so we did the integral, we plugged in top minus bottom, and we got a positive number, something bigger than 0. What do you think that tells you about the area on the graph that we were shading? Yeah. Most of it is above. Okay, because you can still have some below, it's just if it's less below, it can't cancel out up above. Okay, so if the area is bigger than 0, meaning positive, most of the area is above the x-axis. Specifically on that interval, like from A to B, because that's the only section we're concerned with. What if the area value we get is less than 0, meaning negative? It's under. Yep, most of the area is below or under the x-axis. Okay, and then the 4th option is what if we get an area value of 0? We did all this shading, and in the end, the area value was 0. That's not saying you don't have any area, because you were physically able to shade, right?
Area over and under.
They're equal, okay? So, same area above and below the x-axis. Do those 3 kind of scenarios make sense? Those are our only 3 possibilities. When we calculate the area under the curve, it's either going to be positive, negative, or 0, and based off of those, we can determine kind of where the area is located. Okay, so what we're going to do is just practice some of these antiderivatives today. Can we get a graphing calculator out? I'm going to show you how to do antiderivatives on the calculator really quick and easy, but we still need to know how to do them by hand because sometimes you might not have a calculator handy. Okay, let's try this first one. So using the fundamental theorem of calculus, we're going to first find the antiderivative, okay, work backwards, and then we're going to plug in those bounds. Okay, but let's tackle the antiderivative first. If you have a 2x, what did you have previously? Before you took the derivative? Yeah, x squared. All right, the next term we have is an x squared. What did you have previously? Yeah? 1/3 x cubed. All right, do we need the plus c? No. Why? Yeah? You know the bounds, okay? So we're going to end there. We're going to do that little bracket symbol and just rewrite the bounds. So now that we found the antiderivative, yes? Yes. Now that we found the antiderivative, we're going to plug in those bounds. Which one do we plug in first? Yeah? Top, right? Top minus bottom. All right, so if we plug in 2, let's see, 2 squared, we'll have 4. And then plugging in 2 into the next term, 2 cubed is 8. 8 times 1/3 would be 8/3. Okay. Now we need to subtract what we get when we plug in the bottom bound. Bless you. Let's plug in -1. -1 squared is 1. -1 cubed is -1 times a -1/3 would change to a positive 1/3. Alright, so let's simplify. Distribute that negative. Let's maybe do the whole numbers first. We have 4 minus 1, which would be 3. And then let's combine the fractions because they have that common denominator. -8/3 minus 1/3 would be -9/3, aka -3. 3 minus 3? 0. Alright, so what's that answer telling us about the area under this 2x minus x squared graph from -1 to 2? Yeah? You have the same area above and below. It's canceling each other out. Okay, so let's go ahead and see if our calculator can give us the same value, because you are able to use the calculator on some portions of the AP tests. Okay, so go ahead and turn your calculator on. Do we remember how to find the derivative button on our calculator? Remember we did that at the beginning of the year earlier? Which buttons do we press to find the derivative option? Math. And if you scroll down, the derivative is option 8. You see how it says deriv? Go ahead and take a look at 9. You see how it says int? That's for integral. So go ahead and select number 9. And hopefully you have the integral symbol pop up with the little boxes. Okay? What we're going to do is just type in the function or the integral that they provided for this example. So we'll type in -1 for the bottom bound. Use your arrow keys to jump from box to box. We'll type in 2 for the upper bound. Our function is 2x minus x squared. And we need a dx on the end. So when you type in the integral, it should look exactly like it does on your paper. Hit enter. Now this is given to us in scientific notation. If we were to move that decimal place 14 spots to the left, isn't that really close to 0? Yeah. So it's practically 0 like we had here. Okay, so it seems to be checking out. Alright. Let's go ahead and try the next one. Now, the fundamental theorem that we discussed yesterday, remember how we said it had to be continuous and differentiable on an interval? It had those stipulations. Okay? Sometimes you might have to be careful about the function they give you. Okay? If you were to take a look at this function, can you think of a value for x that would present a problem? Yeah? 0. Is that x value of 0 within the bounds of your integral?
Yes.
Yes. Okay, so if that value is a problem, there's some type of hole, jump, asymptote, sharp point, something like that going on because it's presenting an issue. If it's in the interval, we cannot figure out this area because it's not continuous or differentiable between -2 and 3. Bless you. All right, so we'll go ahead and say write down the x value of 0 is an issue. Okay, it would make the denominator 0. So the function is not continuous. Okay, for this particular case, we would have some type of asymptote there. So we cannot evaluate the integral. Okay? If you don't believe me, try to type it in on your calculator. Depending on how fast your calculator is, it's going to take some time for it to think about it, but eventually an error message would pop up. Okay? And the reason that error message is popping up is because we have that issue value between the bounds. Okay? Does that make sense? So we're not even going to worry about that one. We're not even going to work backwards for the antiderivative. Sometimes they're easy, you just got to make sure that you can recognize that. All right? For instance, let's check out the next one. Is there an x value that would be an issue for this one? Is there a number that wouldn't work? Yeah.
0, but 0 isn't on the interval.
There we go. All right, so even though 0 is an issue, it's not within the bounds. So we should be able to work backwards from this and figure out the area. Okay? Can we rewrite this somehow? Instead of having a fraction, can we make it look a little easier for us to find the antiderivative for? Yeah.
X to the power negative 2 times 2x plus 3.
Okay, so let's go ahead and bring up that x squared. We'll make it a power of negative 2. And we're still left with the 2x plus 3 quantity up top. I like it. Maybe let's distribute in that x to the negative second. Okay. If we're going to multiply it into the first term, we got to add the powers together. So that would be an x to the negative first. And if we distribute it into the 3, that's just a 3x to the negative second. Okay, so the fraction's gone, which is good. The parentheses are gone, which is good. Let's go ahead and try to work backwards. So what's our kind of thought process for the antiderivative? You kind of had those two steps to do. Yeah.
We need to add 1 to the power.
Yep.
And then divide the coefficient
By the new power.
Yes.
Okay. So let's go ahead and add 1 to this power. Negative 1 plus 1 is 0. And then you have to take 2 divided by 0, that new power. Can you do that? No. Okay. That doesn't mean this doesn't have an antiderivative. It just means it's a special antiderivative. You can't find the antiderivative using that process. Can you think of a special antiderivative? Maybe you want to rewrite this as 2 times 1 over x, right? You have a negative power, you can move it to the bottom. If you work backwards from 1 over x, what was your original function? It's a special one. Yeah?
2 ln x.
It's a natural log. If you take the derivative of a natural log, you'll get 1 over x. Okay? So we have 2 natural log of x. If we work backwards, that was a special one. Didn't really fit that 2-step process. Let's try this one though. If we add 1 to the power, that would be negative 1. If we divide 3 by negative 1, that checks out. So we have negative 3x to the negative first. All right, and we're going to evaluate that from 4 to 1. Which bound do we plug in first? The top bound, yep, okay. So we'll have 2 natural log of 4 minus 3 times 4 to the negative first. Then we have to subtract what we get when we plug in the bottom bound. So 2 natural log of 0 minus, or sorry, 1 times, or minus 3 times 1 to the negative first. Alright, now you may have to use your calculator from there because we have some negative powers, natural log values, but let's see if we can get a decimal answer in the end. Bless you. I want you to round to 3 decimal places all the time. That's what you have to do on the AP test. So you can either round or truncate, but you got to stop at 3 decimals. Anybody get a number? Willing to give a shot? What'd you get, Dan?
5 minus 0 to
2, 3 or 2, 2, right? However you want to round or truncate. Can we get that number? Yeah? Okay. Maybe check it on your calculator, okay? If you had a calculator available, a graphing calculator at least for this particular example, you can go to Math, choose option 9 for integral, and just type in the problem the way it looks on your paper. From 1 to 4. Now we do have to be a little careful because this one's a fraction. You have to make sure that you put the numerator in parentheses because you want both of those terms divided by the x squared. But notice how you get the same decimal. So we know we're doing the calculus correct by hand with that antiderivative. Alright, do you guys think you can try the next one? Can we work backwards from trig? Give it a shot. I want you to do it by hand, but remember, check your work on the calculator. Make sure you can get the same answer. Alright, any takers on the antiderivative? If you work backwards? If you have a 2x, what did you have previously? Good, Braden?
X squared plus sine.
Good, okay. Work backwards from cosine, you have sine. Good. All right, we don't need the plus c because we know the bounds. Let's do top minus bottom. So we would have pi squared plus sine of pi minus 0 plus sine of 0. All right, so unit circle, sine of pi that's your leftmost point. What's our sign? Go ahead, Dan.
0.
That's 0, yep. And then we have minus 0, and then minus sine of pi if we distribute that negative, or sine of 0 if we distribute that in. What about sine of 0 on the right-hand side?
0.
That's 0 as well. Yep, so it looks like in the end we're left with pi squared. Now if you type this in on your calculator, okay, exactly the way it looks, you should get pi squared as a decimal, which is 9.869 or 870 if you rounded. Okay. How'd you do? Pretty good? All right, we're going to continue with these antiderivatives, okay? But we're going to kind of change what's given to us, at least the information we know. Instead of having to work backwards from an equation to help us figure out an antiderivative, we may have to work backwards from a table, which is a little bit different, but still a possibility for us to do, okay? Now, if you look at this table, we have different x values, and we know different function values, depending if it's the original function, the derivative function, or the second derivative, okay? So let's go ahead and check this out. What is the value of this integral? Okay, they're asking us to figure out the area under the derivative graph from -3 to 1, okay? And notice how it says what is the value, not what is approximately the value. If it said approximate, you could use rectangles or trapezoids to divide up that table like we did the other day. But since it's asking what is the value, we need to know this exactly. So we're going to use that fundamental theorem of calculus. So let's first tackle the antiderivative. If you work backwards from f prime, what kind of function did you have before? Yeah? F, the original function, yep. So our antiderivative is f of x. We don't need the plus c because we know the bounds. So let's just go ahead and rewrite the bounds with that bracket. Okay. Which bound do we plug in first? The top. All right. So if we plug in 1, that would represent f of 1. And then we need to subtract what we get when we plug in the lower bound, which would be f of -3. Do we know either of those values based off the table? Yeah. F of 1 is -2, and f of -3 is 4. So it looks like our area value is -6. Okay? So even though we don't have a graph to go off of, we don't have a function to go off of, we still have a table to go off of. So this is basically telling us the area under the derivative graph from -3 to 1 is mostly underneath the x-axis. There might be some above, okay, but it's mostly underneath because our overall answer was negative. Okay, let's go ahead and try, thank you. Let's go ahead and try the next one. Okay, kind of similar. We're going to work backwards from our functions. What's the antiderivative of f prime? If you work backwards from that, wouldn't that be your original function? Okay, but notice how we also have to work backwards from the second derivative. The dx on the end is just telling you when you stop working backwards. Okay, so what if you work backwards from the second derivative? What was your previous function? The first derivative. Yep. We don't need the plus c because we know the bounds, so we'll throw in the bracket with those bounds. So now we need top minus bottom, which would be f of 3 plus f prime of 3. That's what we get if we plug in the top, minus f of -1 plus f prime of -1. We have top minus bottom. Alright, so we could figure out those values based off the table. F of 3 was 1. F prime of 3 is 3. F of -1 looks like 0. F prime of -1 is 1. So it looks like in the end we have an integral or area value of 3. Sometimes I think these tables are a little bit easier to do. You don't have to go through like add 1 to the power, divide by that new power. Those can be a little tricky. But the tables are a little bit easier. Let's try the next one. Okay. You guys see how we have that 3 in there, that coefficient. Okay. When it comes to the antiderivative, and we'll talk more about this in the next section, but that 3 coefficient can just stay there. Kind of carries from function to function. Yeah. Sure. So we really just have to work backwards from the second derivative. What did you have before that? Are we thinking the first derivative? Okay. So we'll write f prime of x. No need for the plus c, because we know the bounds. Let's do top minus bottom. So we need 3 f prime of 5 minus 3 f prime of 1. Based off the table, f prime of 5 is 2, and f prime of 1 is 0. Looks like we get 6. Do you guys think you can try the next one? Okay, that 1/2 and 2 are coefficients just like this 3 was. So you can leave them in the antiderivative when you work backwards. Okay, go ahead and give 4 a shot. How does 8.5 sound? Pretty good? Are we doing okay with the table? It's a lot of jumping, but you gotta just keep on track. Yeah.
Oh, never mind.
You're okay?
Yeah, I just realized what.
Okay. Alright. Alright, let's take a look at 5. A little throwback here. Write the equation of a tangent line. What do you need to know? Have I beaten it in yet? Equation of a tangent line? Point and slope. Alright. Point, slope. Alright, now we're going to tackle 2 different types of this problem. If we have time today, maybe divide this space in half on your paper because we're going to try another example after this one. Notice how in these directions it says to the graph of f of x. So we need the point on f of x at 3, and we need the slope of f of x at 3, aka meaning the derivative. What do you think, Dan?
The point would be 3, 1.
Yep. Okay.
The slope would be 3.
And the slope would be 3. All right, so your point value is 1 based off the table, and your slope value based off of f prime would be 3. Putting those together in your point slope form, we got y minus 1 equals 3 times x minus 3. Hopefully that type of question is pretty simple for us by now, okay? But let's go ahead and try to think about this. What if the direction said, I'm going to write them over here, the graph of f prime of x at x equals 3. Okay, so we're still finding the equation of a tangent line, but this time it's asking about the derivative graph, not the original graph. Where would the point and the slope come from for that slight change of direction? What do you think, Dan?
As we did for the initial f of x, you would just do the same. So f prime, your point would be 3, and f prime prime would be negative 3.
Okay, so we're changing which function we're focusing on. This one is the derivative function, so we need the point on the derivative function, which would be f prime of 3, but then we need the slope of the derivative function, basically the slope of a slope, aka the second derivative. Notice how the slope is the next derivative after the point function. Okay, so based off the table, f prime of 3 was 3. The second derivative at 3 was negative 3. So you can put those together to write your equation. Y minus 3 equals negative 3 times x minus 3. So a lot of 3's. Alright, are we okay with that slight change? Okay, you got to be careful as to what function they're asking you to write that equation to. Alright, last one for today. Use the equation of the tangent line in number 5. Okay, we're going to focus on this main one that they wanted us to do to approximate the value of the function at 3.1. What do you feel like doing? Go, Dan?
Plugging in 3.1 for the x value.
For the x value, yep. This is the equation of the tangent line at 3. We're going to use it to approximate the value at 3.1, which is really, really close to 3. So let's go ahead and plug it in for the x value. 3.1 minus 3 is 0.1. 0.1 times 3, 0.3. Add the 1 over, we get 1.3. Alright, so the function value at 3.1 is approximately 1.3. Over or underestimate? This is kind of a throwback question as well. I remember doing this with you guys before I left. Yeah.
If you look up at the equation chart and go to where 3 was, the concave at that area, which would be 3 prime prime, was negative, which would mean that the estimation would be over. As any double prime thing being negative makes fx concave down.
Okay.
And any estimation on a concave down object, the estimation line or value is going to be an overestimate.
Wonderful. All right, so let's simplify that. What we're going to do, I get him, but I'm not sure if some of you did. We were drawing a tangent line to a graph. The graph, though, the shape of the graph is important, whether we draw a tangent line on a concave down or a concave up. So what we have to determine is this particular f graph that we're focusing on at this point of 3, is it concave up or concave down? That comes from the second derivative, if it's positive or negative. So notice how at that x location of 3, the second derivative is negative. Therefore, we have a concave down graph. So we'll say f double prime of positive 3 is negative 3. So f of x is concave down at that point. And notice, if you draw a tangent line on a concave down graph, the tangent line is above the graph. So this would be an overestimate. Does that ring a bell to us from earlier this year? Okay. So we'll say the approximation is an overestimate. Perfect. All right. That's it for this section. Tomorrow we're gonna have a free response day. So we're gonna put you in your little groups and try to talk through some free response questions, and we'll go over them tomorrow. Okay? I believe we have one more section to go over until we're halfway through this unit. So try to anticipate a partner quiz sometime next week. Okay? We still have one more section and one more free response day yet to get through before that happens.